The Royal Swedish Academy of Sciences has today decided to award the 2021 Nobel Prize in Physics for groundbreaking contributions to our understanding of complex physical systems. One half of the prize is awarded jointly to Shukuro Manabe and Klaus Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. The other half goes to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales.
From a distance, complex physical objects can appear simple. From atoms to planets, taking a closer look always reveals structure. We are awash in complexity at every scale that we observe. As scientists, we ask, how much detail is required to explain the observations? Must we track every water molecule to explain the ocean? What length scales are important to understand if we are going to see what phenomenon emerge from such a system? One half of this year's prize focuses on the physics of Earth's climate. That's an old topic in physical sciences. It began in 1824 with Fourier. Fourier recognized that the atmosphere of Earth is ostensibly transparent to the visible radiation from the sun. And yet the Earth converts that visible radiation into what he called dark heat, the dark energy of Fourier's time. He surmised that this must interact somehow with the atmosphere to keep Earth warm. Scientists subsequently measured in the laboratory the absorption and emission of what we now call infrared radiation, Fourier's dark heat. And it was to take 70 years before Svante Arrhenius took these observations and these measurements and combined them in the first mathematical model of climate. And he predicted that if the concentration of greenhouse gases in the atmosphere increased, so too with the temperature of the Earth. Another 70 years, 2 world wars, and the computer revolution would pass before Shukuro Manabe and his colleagues knit together this web of processes, including key aspects of the atmosphere's thermodynamics and dynamics, and made the first prediction, reliable prediction, that if you double the carbon dioxide in Earth's atmosphere, the Earth's surface temperature would increase by 2 degrees Celsius. And about the same time, Edward Lorenz taught us about chaos, that the weather is chaotic. It evolves rapidly and becomes unpredictable after about a week. Could it be that Lorenz's chaos was noise to the climate? So thought Klaus Hasselmann. He made the analogy between the rapidly varying weather and the slowly varying climate and Brownian motion from Einstein's theory, whereby rapid collisions of water molecules with pollen grains displace them slowly over time. He then predicted that the weather on timescales of days influences the ocean on the timescale of years. He went further with these ideas, and he constructed a systematic statistical way to compare measurements, observations, and models to extract the fingerprints of particular physical processes in the climate system. Galileo peered into outer space with his telescope. Giorgio Parisi peered into inner space with mathematics and asked questions about apparently banal materials like glass that were deep and impacted many areas of physics. We're used to taking a liquid like water and cooling it under normal circumstances. It freezes into a periodic, well-ordered structure. However, if we freeze the liquid very rapidly, it becomes another body. We call it amorphous. It has attributes of both solid and liquid. We can understand the difference between these systems in daily life because we see them in glasses all the time. Glasses fracture like a solid and yet flow like a liquid. We can consider their energies, their energy landscapes. The periodic solid has a simple landscape. A particle in a bowl can only find one place to rest. In a glass, the landscape is complex and rugged. It's not clear where particles will reside. They are frustrated. Giorgio Parisi studied a magnetic version of a glass called a spin glass. Imagine that we can decorate this triangle with magnets that can either have their north poles up, north poles down, or they can flip between north up and north down. Okay. However, we have the stricture that no two corners can have the same orientation. So when we place the third, it breaks the stricture, it breaks the rule. So another one must flip, which drives the flipping of another one, and so forth, forever. The system is perpetually frustrated. Giorgio Parisi tamed this frustration, this complicated landscape, by building a deep physical and mathematical model which was so broad that it has impacted a vast range of fields far beyond spin glasses. From how granular materials pack, to neuroscience, to how we compute, to random lasers, and to emergent phenomenon far beyond what he envisioned in the 70s when he started this work.
Thank you very much, John.